We're going to have just a short additional lecture here talking about the choice of window. In our previous analysis, we used a window that was either ones or zeros, and that was it. So I have modified the code that we were looking at last time. Everything is the same so far. And then we rerun periodogram and pwelch. But this time we're using the Hamming window. The Hamming window is a tapered window. I think you can see this. WV tool win. We'll show you this window as soon as it finishes running. There we go. The Hamming window here on your left peaks at 1, tapers down to almost 0 at the edges. And in the frequency domain on a log scale, it has this main lobe here as what we call that. We would like that to be as narrow as possible. There are two ways to make it narrow. One is to change the window shape. The other is to change the window length. Changing the window length, increasing the window length, decreases the width of what we call the main lobe until eventually it looks like a impulse as we get infinitely long. When you get shorter, the width of that matters. So why does it matter? It matters because when we multiply a signal segment or a signal by a window, we convolve it in the time domain. And so that means we take whatever the true spectrum was and we convolve it with this, which is going to blur it in the time domain. In addition, we have these side lobes. The side lobes for the Hamming window are only down about 45 dB from the peak. And they don't decrease much after that. Different windows have different characteristics. So I've run this code because it takes a little while to run. So we're ahead of the game now. And we get two outputs. The first is with the rectangular window. It's over on your left. And over on your right, we have it with the Hamming window. Now we wouldn't expect too noticeable of a change on the sequences that are taken at the full width. I'm sorry, the FFTs, or the analysis on the full signal. But the Welch power spectral analysis in the bottom half of each figure does show some interesting differences. So over here on the very left, we see that we've got a power spectrum density of about 1, which is what it should be. Over on the right, it's about the same, but now it's much smoother. So we can cause things to be smoother by averaging more, or we can cause them to be smoother by using a different window, and we use a different window in this case. Well, the windows really make a difference when we start to analyze tones. So here I've created a tone of length 128, and I'm going to use an FFT length of 1024. So every time we take the FFT, we're just using a longer one. We're zero padding it, and that's what that does. So we're using the periodogram in every case for this analysis, and the reason why we're not using the Welch method is because the Welch method reduces the variance of the spectrum when you have a random signal at the input. Well, the cosine isn't a random signal. Now, what would happen if we had cosine plus some noise? Well, then using the Welch system would be advantageous. But right now we're just using the straight periodogram, which means we're taking the FFT of the entire 128 samples, and we're doing it with a 1024 length FFT. So we will, after we're doing that using the rectangular window, the triangular window, and then the Hamming window to see the different effects. So let's run this and observe what comes out. Okay, so on the left-hand side, we plot the first 100 samples of X, and then we plot the FFT. And the FFT looks pretty good in almost every case, but one thing you'll notice is that there are little, what we call side lobes. Let's zoom in on that. Some side lobes right here at the bottom in the rectangular window case. We don't really see any in the Hamming window. Well, they're there. They're also there with the triangular window. It's just the scales are such that they're hard to see. So we're going to go now over to the figure on the right, figure 8, and we can see with the on a log scale, we can see that the rectangular window has some pretty high side lobes. They're kind of comparable to the main lobe. So when you have a single frequency, we really don't care, but what would happen if we had multiple tones in the same signal? It would be hard to distinguish the tones, the additional tones from the side lobes of the largest one. The triangular window has a broader main lobe and but the distance between the peak side lobe, which there is at minus 27 versus a peak of 27, so that's 54 down. And this is, with the rectangular window, 30, and we're about minus 0.8. So we're a significant difference here in the peak. And I realize as I look at those numbers I've made a mistake in the code. Since we're dealing with powers already, I should have, converting to dB, I should have used 10 times the log instead of 20 times the log. So I'm rerunning that. Everything will be the same, it just changes the scale to be what we'd like, because what we'll find is that with the rectangular window, the side lobe is about 13 dB below the main lobe for the first side lobe. For the triangular window, it's much lower. It's about 26 dB down from the main lobe. For the Hamming, it's even further yet, closer to 45 dB down. So the trade-off is that the main lobe of the Hamming window is much broader. So we've kind of blurred our spectrum, but we have fewer spurious peaks. Now if we do this same analysis with, say, an additional tone, that's 0.1 times cosine 2 times pi times f times 1.05 divided by fs times t. And now we can run the same code section again. And what do we get? We would really like to see two tones. We know there are two tones. We can't see them. Why? It's just too close together. So let's change this and keep going up until we can start to see them separating. And we'll notice that they separate first on the rectangular window. Do we see two separate tones yet? No, we don't. We can tell that we've actually added them because we're seeing the beginning of what we learned to recognize as the beat effect in frequency analysis. Let's go with 1.2 and see what we're doing here. So here, it's kind of hard to tell what's going on. It looks like we have two tones, perhaps, in using the rectangular window. We have a big main lobe and then we have the smaller one off to the side, but we aren't quite sure is this one of the side lobes of our original signal? In this case, it's not. So we're starting to see something. The Hamming and the triangular window are also showing something, a little bit of a hiccup here on the side, telling us that we might be having that second signal come in. Now, if these were closer in amplitude, in fact, let's just try that. If they're closer in amplitude, then there wouldn't be so much ambiguity. And in fact, you would begin to see the two signals. So the reason we went through this exercise is just to show that, actually we may as well step back and complete the whole thing. Go back to 1.1 and we'll see that with the windows, when you have multiple tones, you're getting the hint that there might be multiple tones here in the rectangular window, but you have no hint of multiple tones at all in the Hamming window. So we're right here, and we find that the rectangular window works better for distinguishing two tones, whereas the Hamming window works better for keeping down the side lobes. Whoops. That's going to not do what we want. We want to run section. There we go. Let's see, that was 1.12, 1.5. You can get the thing by running multiple samples. Okay, so three examples of different windows that you could use. Nobody really ever uses a triangular window. The Hamming window is commonly used for speech and audio, but it's not good for everything. The rectangular window is the default, and you get higher resolution than you will with any other window, but the cost is that you get side lobes to go with it. So I'm going to post some extra slides prepared by another professor that provide some more examples and a little bit look at this that may be useful as well. Thank you.